So, today our topic is quantization of speech signals. Now, whenever we would like to have any waveform approximation coding, or even for parametric coding also, one of the essential steps that we require to store and process the digital samples is quantization. So, before quantization, of course, we require sampling of the speech signal. So, if we say that the speech signal is given by x as a function of time, in that case we are going to sample the speech, where the samples will be denoted by x n t, where t is the sampling period and n is the index of the sample. So, we have n that varies from, I mean, if we start the sampling from n is equal to 0, then n is equal to 0, 1, 2, etc., etc. So, that means to say that at those time instances, means x of capital T, x of 2t, x of 3t, etc., there we are going to sample the speech signal, and those samples, okay, which we can later denote by x of n simply, where n happens to be an integer that goes from 0, 1, 2, etc., and we denote the speech samples by this, and each of these samples are thereafter quantized, and it is actually represented by just a set of discrete levels. So, in the process of quantization, what we have is actually a mapping from the input variable space to the quantized variable. So, if we tell the input variable as the variable x, then we indicate the quantized variable as x of cap, okay, x cap, and this input variables x we can denote by, I mean, there may be several I mean independent steps for this. So, we can say that this is x1, then this is x2, then this is x3, then this is x4, x5, and so on. These are the steps that we have along this x, and the corresponding value that we would like to have for the x cap again will be in the form of different steps. So, we may say that say this could be our x of 2 cap, then this could be, I mean x of 0 or x of 1 cap could be here, and then x 2 cap, x 3 cap, x 4 cap, and so on, they are indicated as shown. So, actually what we will have is that if we have on the negative side also, we have the steps as minus x1, minus x2, minus x3, minus x4, and so on. Then if it is what is called as a mid-trait quantizer, then we have that when the value is from, rather I mean it is better that we call this as x0, x1, x2, x3, and so on. So, that when the input signal is between x1 to x2, then it will be denoted by the level x1 cap. So, this is the input and this is the quantized variable. So, x cap is actually the quantized value of x. So, when it is between x1 and x2, then its quantized value is x1 cap. When it is between x2 and x3, then its value will be x2 cap. Between x3 and x4, we would like to denote it by x3 cap and so on. And likewise, on the negative side also we can have, like here we can have minus x1 cap, then minus x2 to minus x3 we can have minus x2 cap, minus x3 to minus x4 we can have minus x3 cap and so on. Okay. So, this essentially realizes what is called as a mid-trade quantizer. And similarly, there may be what is called as the mid-riser quantizer, and the mid-riser quantizer will have the steps like this, that here there is no level that is at the 0. Here you can see that it is a mid-trade. So, corresponding to the value of input between minus x1 to plus x1, we have the quantized value as x0 cap, whereas in the case of mid-riser no such x0s will be existing, rather the quantization would go on like this, like if we have this to be, let us say, x0, then we have this as x1, then we have this as x2, x3, x4 and so on. Then corresponding to the signal between x0 and x1, we can have the quantized signal as x1 cap, x1 to x2 we can have this as x2 cap, then x2 to x3 we can have as x3 cap, and on the negative side also we can have this as minus x1 cap, then here we can have minus x2 cap. So, that if the signal is between minus x1 to minus x2, then we can denote it by minus x2 cap level, and this we can denote by minus x2 to minus x3 could be minus x3 cap and so on. So, this type of quantizer we will be calling. So, this is the input variable and this is the quantized variable, and this kind of quantizers, they are referred to as mid-riser quantizers. Okay. Now, in fact, the quantization step size, if we denote by a quantity delta, then that is actually defined as xi minus xi minus 1, that is equal to delta. So, this is the quantization step size. So, delta is nothing but the quantization step size, and likewise for the quantized values also a similar step size will be there. So, we can also write xi cap minus xi minus 1 cap, that means to say that the difference between these two quantized levels, two successive quantized level, that also will be equal to delta, right. And now we assume that we have the number of levels, okay, that is to say the number of quantization levels we say as 2 to the power b, okay, where b is the so where each of the samples or each of the quantized values are represented by b bit binary code word. So, we have a b bit binary code word and the number of levels will be 2 to the power b. So, what we can have is that the number of levels being 2 to the power b, okay, and if we assume that the samples now we are indicating by x of n, where n is an integer. So, x of n can vary. Let us say that it is going to have a dynamic range of minus x, some value which we can call as minus x max, to let us say that it can go up to plus x max. So, it is minus x max to plus x max is the complete variation that is possible in the signal level, and we can denote x of n as as the mod value of x of n, because x of n can be positive and also it can be negative. In the negative side, its minimum value could be minus x max, and on the positive side it could go up to plus x max, so that the overall so that we can represent the same thing as mod of x n is less than or equal to x max. And then if we have a total variation from minus x max to plus x max, then this entire dynamic range, if we want to make use of this entire dynamic range for quantization, then we can say that minus x max to plus x max, which means to say that 2 times x max, okay, that is going to be delta, that is to say the quantization step size into the total number of levels, that is 2 to the power b. What is delta into 2 to the power b indicating? Because delta is delta being the delta being one step size and 2 to the power b being the number of total steps, then delta into 2 to the power b is nothing but indicating the overall range of the signal, which we have assumed to be 2 to the power which we have assumed to be 2 x max, if the variation is from minus x max to plus x max, as we just now said. Okay. Now, the quantized samples as such we are going to represent by, individual quantized samples, then we will be calling as x cap of n, means whatever, so corresponding to the sample x of n, its quantized value is going to be written as x cap of n. Okay. Now, x cap of n will be equal to x of n only when there is no quantization error, right. So, x cap n will be equal to x n provided there is no quantization error, but think that when you have a quantization step size, okay, take any of these cases, mid riser or mid trade, whatever, you can see that when you take any such value of that lies in the middle of this x 1 and x 2, let us say that we take some value over here. Okay. Now, its actual value is this much, but because of the quantization we have already quantized this to the level x 2 cap. Okay. So, this total step size being delta, so this being equal to delta, that is the step size, you can see that whereas the actual value should have been somewhere over here, we are having the quantized value to be x 2. So, which means to say that the maximum what you can say the quantization error, that varies from minus delta by 2 to plus delta by 2. So, taking the quantization error also into consideration, we would like to write the x cap of n as x of n, that is the original sample, plus a term we add E n, where E n is the quantization noise. And obviously, because delta happens to be the quantization step size, okay, we can definitely express this in terms of the inequality, that E n will then range between delta by 2 to minus delta by 2. Okay. Now, this being the quantization noise, okay, we can assume some simple statistical models for quantization noise. And what are these simple statistical models? First of all, that we assume that the quantization noise is a stationary white noise process. And under this assumption, we can write that the expectation of E n and its product with E n plus m, where m is nothing but a displacement, because E n is the nth sample and E n plus m is a sample that is m samples ahead of this sample E n. Now, E n and E n plus m, okay, they should be ideally uncorrelated. That means to say that if it is a stationary white noise process, then no signal, noise component is going to have correlation with the other noise components, okay, which means to say that E n can have correlation with only E n, and it cannot have correlation with E n plus 1 or E n plus 2 or things like that, E n plus m. So, that means to say that we can write that this is equal to sigma square E, okay, where sigma square E we can assume to be the variance in the quantization noise. So, this is equal to sigma square E for m is equal to 0 and the expectation value is equal to 0 otherwise. So, this otherwise condition obviously takes into account that the quantization noise is completely uncorrelated. So, this is the first assumption that we are making about the statistical model of quantization noise. The second and a very valid assumption is that the quantization noise is uncorrelated with the input signal. So, this also we write that the quantization noise is uncorrelated with the input signal. So, how do we express that mathematically? We have to write again in terms of expectation only. So, we have to take the signal term will be denoted by x of n and the noise term will be denoted by E of n. So, we can write the correlation property as E of x of n into E of, we take for any m, we take E n plus m. So, we take the signal and this is the error or the quantization noise component which is for the n plus mth sample. But because we already said that the quantization noise is uncorrelated with respect to the input signal, its value is going to be equal to 0, okay, for all values of n, for all values of m. Okay. So, no matter even if m is equal to 0, we have x n E n, even x n and E n should be completely uncorrelated with each other, okay, and take any other E n, take x n E n plus 1 or x n E n minus 1 or x n E plus 2, anything, these are going to be uncorrelated. So, this is the second assumption that we are making about the statistical model of quantization noise, and the third is that the distribution of quantization errors is uniform over each quantization interval. So, the distribution of quantization noise is uniform. And it is uniform over all quantization intervals, for each quantization intervals. and we are going to express that as the probability density function of E. So, P E with respect to E. So, the probability density function of the quantization error, and because it is uniform, how we are going to write? We are going to write it as 1 upon delta, delta being the step size which I already mentioned. So, this is equal to 1 upon delta, where the value of E is going to E or E n, whatever you write. Now, we are not writing E n every time, we can write it as P E directly. The value of E rather lies between minus delta by 2 to plus delta by 2. So, this is the range of the quantization errors, and definitely the uniform uniform probability density function would require that it is P E of E is equal to 1 upon delta, and this is equal to 0 otherwise. Okay. So, it is of uniform PDF. So, you can say that if you sketch it, it would be like this, that here it will be delta by 2, here it will be minus delta by 2, and this height is going to be height is going to be 1 upon delta. Okay. So, this is how you are going to plot if E is there, and if P E of E is plotted like this, then you are going to have a uniform distribution, something like this. So, this is the third property. So, three very important, not property, rather I should say assumptions. Okay. So, what are the assumptions? That it is a stationary white noise process, which means to say that the error samples are completely uncorrelated with each other. Second assumption is that the quantization noise is uncorrelated with respect to the input signal, and the third property and the third assumption that we have made is that it is uniformly distributed. I mean, it may be something other than uniformly distributed also, but of course, there the expression would definitely change accordingly. Okay. Now, it has been well experimented for speech that these assumptions, these three assumptions, they hold good quite reasonably for speech signals, and taking these assumptions into consideration, okay, we can write now the signal to noise ratio of the speech signals like this, that we can express the SNR. Okay, the signal to noise ratio would be written as the signal variance, which we write as sigma square x, okay, because x we are assuming to be the signal, and the variance of the error signal is going to be written as sigma square E. So, it is sigma square x by sigma square E, and sigma square x is nothing but the expectation of E x square n, and that of the error is E of E square n. So, this is the energy of the signal, and this is the energy of the error, and this can be written of course in summation form also, summation over n x square n divided by summation over n E square of n. Okay. And if we take the peak to peak quantizer range to be 2 x max, okay, this we have already shown. In fact, we have already indicated this, that is 2 x max is equal to delta into 2 to the power b. So, from this the quantization step size delta can be expressed as 2 times x max divided by 2 to the power b. Okay. And then one of the assumptions, the third assumption that we have made is that the quantization noise is uniformly distributed, and for uniformly distributed it is a very simple derivation, okay, that we would be having the error or the noise variance as sigma square E should be written as delta square divided by 12. That is how it comes for the uniform distribution case, uniform PDF for the quantization error, and this is going to be expressed as, I mean, if we just substitute this expression, that is instead of delta if we write 2 x max by 2 to the power b. In that case, we directly get it as x max square, okay, divided by 3. It is coming out to be 3 because there is a 2 term over here. So, delta square makes it 4 and there is a 12 in the denominator. So, all total we have a multiplication factor of 3 in the denominator. So, it is 3 into 2 to the power 2b, again because it is 2 to the power b for delta square it is 2 to the power 2b. So, this is the sigma square e term, and now we can what we can do is that we can make this, we can substitute this into our original SNR equation. So, if we substitute this value of sigma square e into x max into this this expression sigma square e into this sigma square x by sigma square e, and in place of sigma square e we write this, then we can write the corresponding signal to noise ratio as, I mean, if we take this to be equation number 1 and if we take this to be the equation number 2, in that case simply substituting equation number 2 in equation number 1, we get the SNR as 3 into 2 to the power 2b, because this expression is coming in the denominator of sigma square e. So, 3 into 2 to the power 2b, that goes to the top, and in the denominator term this x max square is there, and sigma square x which is in the numerator term, if it is brought on the denominator side, then we have to express this as x max by sigma this quantity whole square. So, this is going to be our signal to noise ratio. Now, this is just a ratio, and if we would like to express the signal to noise ratio in dB, we are going to write it like this. So, expressing in dB, we can write the SNR, and let us write within bracket dB. SNR dB would be 10 log to the base 10 of this signal to noise ratio, and this is already expressed in terms of the power. So, this is 10 log 10 sigma square x by sigma square e from its original definition of the signal to noise ratio. So, just taking 10 log 10, and if we are substituting all these things, means instead of sigma square x by sigma square e, if we simply substitute this and then take the logarithm, then we can just very easily verify that it comes out as 6b plus 4.77. The 4.77 is coming, you can well understand that there is a 3 over here, log of 3 to the base 10 happens to be 0.477, and then everything gets multiplied by 10. So, that is why you get 4.77 as the term arising out of that isolated 3. 2 to the power 2b of course is the one that is ultimately contributing to this 6b quantity, and then this x max by sigma x, the term that is left over at the denominator of this signal to noise ratio expression. So, since this is in the denominator and we are taking the signal to noise ratio as 10 log 10 of this entire quantity, the denominator obviously gives rise to a minus sign. So, it is minus 20 log to the base 10 of course as x max by sigma x. So, we can write the whole thing as 6b plus 4.77 minus 20 log to the base 10 x max by sigma x. Okay. And just very simply you can see that if we set our value of sigma x, if we set to be just 4 times sigma x. So, if we set that, then we get the SNR in dB as simply 6b minus 7.2. This we can say as equation number 3. All right. Now, this equation that we have written so far, Okay. This is valid subject to certain assumptions. Okay. And what are these assumptions? The first assumption is that, so we can list that what kind of assumptions we made in this process. First is that the signal fluctuations is rapid. Okay. The signal fluctuation is rapid, and that is why the statistical model of noise, what we have already assumed, okay, those three assumptions which we stated, and the statistical model of noise is valid. Mind you, the statistical noise, I mean the statistical model of noise is valid for very rapid signal fluctuations, because then only you can take that the noise signals are uncorrelated with respect to each other, and noise is also uncorrelated with respect to signal. So, without this, I mean without rapid signal fluctuation, you cannot have that assumption anymore. And the second assumption is that you have delta as small, okay, and only if you have delta to be small, okay, then there is no signal that is correlated with the noise. Okay. Delta is small, so that no signal is correlated with noise. In fact, for large delta, that is what you are going to have. I mean, if you have a very large step size, then your quantization error simply follows your signal. So, then the error, then the noise and the signal, they get correlated with each other. So, if delta is small, no signal is correlated with noise. Okay. And the third assumption is that the range of the quantizer is set so as to match the peak to peak range of the signal. The peak to peak range of the signal. Now, this is a very what you can say, I mean it is a very important assumption. In fact, you must have already seen that we have talked about this sometimes back already, because we have been taking the that delta we were taking to be delta into 2 to the power b, we were taking to be 2 times x max. Okay. So, because we have already taken that, we took this point into consideration, that this range is matched with the peak to peak range of the signal. Okay. Now, for the first two assumptions that we have made, okay, that is reasonably valid, especially for delta to be small. What we require? We require that the number of step sizes should be large, okay, because that is only what can make the delta to be small. So, it is seen that for speech signal, the first two assumptions are quite valid for number of levels greater than 2 to the power 6, okay, and generally for speech signals it is so. For speech quantization, the number of levels should be greater than that of 2 to the power 6. So, definitely that means to say that we will be having more than 6 bits for our representation of the quantized samples. Okay. But one very important aspect of the speech signal is that between the I mean between different speakers, we have a very large variation in its signal strength. Okay. Thus, the signal levels in fact can vary by as much as 40 dB for different speakers, and again for the same speaker, the speech signal level varies drastically between the voiced speech and the unvoiced speech. Okay. So, taking the speaker to speaker variation into consideration and voiced to unvoiced speech signal levels variation into consideration, okay, these two factors leads to the fact that that we really have a very tough task in fulfilling the property number 3, because the property number 3 says that quantizer is said to match the peak to peak range of the signal, but for which signal? If we say that it matches with the voiced signal, okay, for the voiced signal if we can happen to match this range, then whenever the speaker goes to the unvoiced part of the speech, then definitely that range cannot be satisfied, because the unvoiced speech is going to have a much lower dynamic range, which means to say that for the unvoiced part of the speech we are going to have a very poor SNR. The SNR may be good for the voiced speech, but for unvoiced speech it is going to be very bad. Okay. Then if it is matched to one speaker, okay, for a speaker having a good speech signal level, okay, and we change the speaker, instead of one person somebody else talks, okay, over the same speech signal quantization system, then there is going to be a very drastic variation, because the from speaker to speaker also we have a large variation. Okay. So, from this point of consideration, okay, the simple sampling is not the simplest scheme of quantization is not adequate. In fact, we have to go in for something like adaptive quantization, which we are going to talk about in the later lecture. Okay. But now at least we can say that what is actually used for the speech quantization process. Okay. It is generally seen that for high fidelity consideration, B is equal to 11, that means to say 11 bit representation is necessary. Okay. So, B is equal to 11 is necessary for high quality for high fidelity considerations. Whereas, it has been seen that B is equal to 7, okay, with SNR equal to 36 dB provides adequate quality in a communication system. So, this fact we remember. In a communication system, and of course, with a uniform quantizer. Again, mind you that whatever expressions we wrote down, okay, those expressions are valid, okay, for uniform quantization, because only for uniform quantization you can have that delta square by 12 coming in, right. So, now we can see another aspect, that means to say that to take the large variation in the dynamic range of speech signals into consideration, okay, one thing which we employ is a logarithmic encoder and decoder, because by taking the logarithm, okay, we can appropriately take care of the dynamic range, because logarithmic transformation, okay, essentially reduces the dynamic range of the original signal, and then it is easier for us to handle. So, how do we have the logarithmic encoder and the decoder? So, we have to consider the blocks like this. So, logarithmic encoder, decoder, and they will be using a transformation which is given by y of n equal to log mod of x of n. So, we have to realize this, and how do we realize that? we take x of n, that is the speech sample, as an input, and then we have a logarithmic transformation block. So, it is log mod. So, definitely this output will be nothing but y of n. But then after making the logarithmic transformation for the signal y n, now instead of taking the quantization for x of n, we take the quantization for y of n. So, after y of n, after obtaining y of n, we put the quantization, which we just write as q, okay, and this is the quantized output, okay. And then we also take, I mean, because we are taking the modulus, okay, what we have lost in this case is the sign of the original signal x of n, okay, original sample x of n's sign, that must be preserved. So, we have a block, okay, that preserves the sign. So, this is sign of x of n, that is what we will be taking. So, sign value, which is a 1 bit representation, that whether it is positive or whether it is negative. So, this 1 bit information has to be encoded, and then also the quantized value of y n. So, there will be an encoder, okay, that accepts the quantized signal and also the sign of x n, and this gets encoded into the bit stream. So, C n is the bit stream corresponding to the nth sample. Okay. So, this is what we are having at the encoder end. Now, at the decoder end, we must have a corresponding inverse transformation, because here we have made logarithmic transformation. So, definitely to get x of n back, or obviously we will not be able to get x of n directly back, because there is a quantizer in between, and quantizer is definitely going to provide losses. So, instead of x of n, we are going to have x cap of n, which will be ultimately obtained, and that will be obtained at the decoder. So, the decoder block diagram would go like this, that it will accept this C of n, that means to say this encoded bits will be received as an input to the decoder, and then ultimately it has to obtain x cap of n, okay, as an approximated form of x of n. So, the decoder block diagram can be shown here. So, this is C of n coming as an input. Here we have the decoder, then we have y of n, we write it as y cap of n, and then we have here the exponential, because you have taken the logarithm, you have to take the exponential just to get back the signal, and the exponential of this actually helps you to get back the mod value of x of n, okay. Because this y of n what we have taken is definitely the mod value, because we already saw it for the encoder part, that here it is the magnitude of x n which is already taken, and over that the logarithmic transformation has been applied. So, here also we get mod of x cap of n, okay. But C of n contains the sign information also. So, if we extract and separate out the sign information, then what we can do is that we get this sign information. So, this is sign of x cap n, okay, and if we multiply this x cap of n, mod of x cap of n with the sign of x cap n. So, where sign x cap of n is going to be either +1 for positive or -1 for negative, okay. Then we at the output of this multiplier we will be getting x cap of n. So, this is our decoder, okay, and we can write the inverse transformation equation as x of n is equal to exponential of y of n, okay, into sine of x n. Okay. You see, this is exactly what we are going to do. Okay. Only thing is that here we are not saying y n, we are saying y cap of n, okay. But exponential of y cap of n is nothing but the mod of x n, and that is actually multiplied by the sine of x n. In this case, we use the x cap, okay. And we can write from the encoder side, okay. The encoder has got in fact here y n, and then after this, after the quantization of y n, here we are going to have y cap of n, okay. And in fact, y cap of n we can therefore write as the quantized value of log mod x of n. You see, we directly get from here log mod x n and then take the quantized value of that. So, you get y cap of n, which is quantized value of log mod x n, okay, which of course, we can write as log mod x n, okay, and then we can write this as log mod of x n plus epsilon n, because there will be quantization error. So, the quantization error is denoted by epsilon n, and then once obtained, once we obtain this y cap of n, then x cap of n, that is at the decoder end, x cap of n will be written by this equation directly, x exponential of y cap n, okay, into sine of x n, okay. And here we simply have this, I mean exponential y cap n can be written as mod of x n, okay, mod of x n into sine of x n. This directly follows from our encoder, okay. So, where y cap of n we are getting as, or rather to say exponential of y cap n is mod of x n into sine of x n, okay. And then we also have the exponential of I mean, because you see we are taking just this y cap of n, and y cap of n is log of mod x n plus epsilon n. So, this whole quantity is epsilon n we have to take, I mean this whole quantity is exponential we have to take. So, there will be a quantity exponential of this logarithm x n, which is simply the x n, and then there will be another term which is exponential of epsilon n. So, exponential epsilon n is a term that we will be getting outside this. So, this is exponential of epsilon n, and this whole thing mod x n sin x n is nothing but x n. So, this is x n into exponential of epsilon n, okay. And if epsilon n is very small, okay, for very small epsilon n, we can approximate this exponential epsilon n as a linear quantity. So, very small epsilon n, we can write the x cap of n, okay. This whole expression we are making for x cap of n, remember, because we proceeded from this x cap of n. So, x cap of n is this, and for very small epsilon n, I can write this as x n, rather I have to put an approximation sign, approximately equal to x n into, instead of writing exponential n, I mean epsilon n, we write as 1 plus epsilon n, and this is equal to x n plus epsilon n x n, which is equal to x n plus f n, okay, where f n is equal to x n epsilon n, okay. And since x n and epsilon n are assumed to be independent, we have sigma square f equal to, so f n is nothing but the product of x n and epsilon n, and if the noise and the signal they are uncorrelated, which we are assuming, then we can have the variance of this f, that is the product, is equal to sigma square x into sigma square of epsilon. Okay. So that the signal to noise ratio will be sigma square x divided by, in this case we are going to have sigma square x into sigma square epsilon, because it is sigma square x by sigma square f. Okay. That is going to be the error term. So, x cap of n, because x cap of n is x n plus f n. Okay. So, that is why f n is basically the noise term. So, that the noise power is sigma square f, and we have sigma square x by sigma square f, and sigma square f is written as sigma square x into sigma square epsilon. Now, you see the beauty that from the numerator and the denominator, the sigma square x that gets cancelled out, and we simply get 1 upon sigma square epsilon, okay, to be the signal to noise ratio. So, which means to say that the signal to noise ratio in this case, I mean for the logarithmic transformation, by using the logarithmic transformation, we see that the signal to noise ratio is independent of the signal variance. This we did not see for the regular quantizer. Okay, for the linear quantizer we did not see that, but after the logarithmic transformation we see that the signal to noise ratio is becoming 1 by sigma square epsilon, which means to say that it is not dependent on the signal, and it is only dependent upon the quantization step size. Okay. So, this much for today, and in the next class we are going to talk about adaptive quantizers, okay, as applicable to the speech signals. Thank you.